Okay, we continue. I had to break there to answer a question. So, we now are about to do our model updating. So, I recognize that I have 4 things that I want to update. 1, 2, 3, 4, right? But I only have 3 frequencies. So, I'm going to have to use something else. And in this case, I'm going to use the mode shapes. So, we have this model, right? Now, this model, given any parameter values for IB0, IB1, IB2, IB3, the model will predict an omega 1 model, an omega 2 model, and an omega 3 model, right? 4 values of these parameters. The model will also predict phi1 in the model, phi2 in the model, and phi3 in the model, right? And you can, as you can imagine, right, keep only the rows 1 and 3, right? So that your model modes match in location your experimental modes. In addition, you can normalize your modes, right, of the model so that they have norm 1 and are therefore compatible with your mode shapes from the identification. The goal, of course, is to select IB0, IB1, IB2, right, and IB3 to make the quantities that come from the model match the quantities that were identified from the frequency. So we can measure the discrepancy in a number of ways. Let's say that J is the thing that measures our discrepancy. So we could take, we could take, for example, delta frequency, right? That's the change, delta frequency being omega 1 from the model minus omega 1 from the experiment, omega 2 from the model minus omega 2 from the experiment, omega 3 from the model minus omega 3 from the experiment. That could be delta omega, right? So I could say that my error is the norm of delta omega plus. Now I need to put something for the mode shapes. So, and there are many ways to do this. I'm going to do it, let's say, mode by mode. You can write it differently if you want. You can think about it and see what you like. In this case, I'm going to say that there is a delta phi 1 that I can take the norm, right? What is delta phi 1? It is obviously delta phi 1 is going to be my phi 1 from the model minus my phi 1 from the experiment. In this case, that has 2 numbers, right? And I can take the norm, which becomes 1 number. I can say that, however, these vectors that I'm subtracting here are both norm 1, right? So these frequencies could be much bigger. For example, maybe those frequencies are 50. And so I'm subtracting 50 minus, or even, let's say, not 50, 200, right? So I could be subtracting 200 minus 198 or something. So this might be small compared to this, even if the error is significant. So you might want to put a parameter, alpha 1, which is just a weighting that you will add yourself. So you could say alpha 1 times the norm of mode 1 plus alpha 2 times the mode of delta phi 2 plus alpha 3 times the norm of delta phi 3. And then where alpha 1, alpha 2, and alpha 3 are up to you. You could say they are 1, for example. You could say something like this: I really believe my first mode from the experiment a lot. I like it. So I want to make this term important. And so I'm going to make my phi 1 And also because of the delta omegas, I'm going to make my phi 1 10. I kind of believe my second one quite a bit, but not as much, so I'm going to use alpha 2 5. And I don't believe my third mode so much, so I'm going to leave that one as a 1. So these are numbers can reflect the confidence that you have on these values, right? In any case, once you have made that decision with regards to the weighting values, then you have a cost function, right? So what you need now is the same thing that you've done in your model updating code. You have said, okay, I need to write a function that, whose output is j and has a name, my function. And the input to that function must be the parameters that you want to change. So this could be x, right? Where x is a vector that has IB0, IB1, IB2, and IB3, for example, right? And this function does something, and at the end it calculates j, right? Once this function is available, we can then allow fmean search to do the search, right? So we would say x equals fmean search, and then we say start with some x0, which is our guess of what these values are. We don't know, we put whatever. And then, is there anything else? No, I think that's it, right? Fmean search. No, I think that's it. Let me double check to see if my mind is slipping for some reason. Oh yeah, I knew I was forgetting something. So it's fmean search, parentheses, at my function, otherwise how is it going to do it, right? At my function, then comma x0, right? So this is the name that you do. So the search code that does optimization takes an initial guess, goes into this program, calculates the j, tries to improve by reducing the j until it can't do it any further, and then it tells you what the output is, and this x would contain the values of IB0, IB1, IB2, IB3 that the program could find. Now, in this case, we can hope to find 4 things. Why? Because we have more than 4 constraints. We have 1, 2, 3, 4, 5, 6 things. If we only had frequencies, we could not attempt to find 4 things because there would be infinite solutions. Okay? So that's it. I had one more thing, which was to talk a little bit about the noise, but I think I'll leave that for next time, because your next homework, it's still going to be, well, no, actually no, I take that back. Let me just take a minute to mention it. Now, just in case you need it, for the homework that I am planning to give you. It really is not much. So the question is, when you do system ID, remember that you take a singular value decomposition of the Hankel matrices, and the program will actually output the important singular values, and in the case of something, you would see something like this, right? So in ideal cases, this is a huge gap between these singular values and these singular values, and so you conclude that the order is 4 and everything is well. Now, one of the things that will happen in the case of a stochastic identification is that there will never be such a huge gap, because even if the system was 4, maybe like this. So you might see a small gap, and that gap is going to get larger and larger as what? As the duration of the signals get larger and larger. So if instead of using 2,000 points, you use 20,000 points, the gap might be a little bit bigger. If instead of 20,000 points, you use 200,000 points, it might be bigger. Why? Because the expectation values are becoming more and more accurate. Okay? Now, in general, it may be that you're not sure what is the order. So, you may find, let's say, something like this. And you say, well, there's nothing very clear, but I'm going to take this. 1, 2, 3, 4, 5, 6, 7, 8. And you take 8. Now, when you do that 8, you go and you calculate your eigenvalues, right? So you have lambda 1 and lambda 1 conjugate, lambda 2 and lambda 2 conjugate, lambda 3 and lambda 3 conjugate, lambda 4 and lambda 4 conjugate, right? Okay. Now, you look at this lambda 1 and this becomes omega 1 and sigma 1. This one becomes omega 2 and sigma 2, omega 3 and sigma 3, omega 4 and sigma 4. Now, let's say that this sigma 1 is 0.05, this is 0.03, this is 0.01, and this is 0.12. Well, if that were the case, most identification experts or people that know about this thing and so on would say that the fourth mode is probably not a good mode. We would consider this to be a computational mode, meaning it is an artifact of the noise. It is there because we are processing data. It does not really reflect a physical quantity. Therefore, we may discard this mode because the damping is too high. So in the end, we normally need to discriminate between modes that we trust from modes that we don't trust. In the examples that you've done before, this is obvious because there's huge gap and it's clear that all this stuff is really good. But in actual practice, it may not be so. And so you find yourself having to take some sort of a guess of a bunch of things, and then from the bunch that you take, you want to discriminate. Now, the simplest discriminator is damping, because we know that in our physical structures the dampings are small. And so if we find a damping on the order of 10% or more, we immediately assume that that mode is unreliable and that it's computational, and we discard it. When we have modes that are well separated, we also expect that our mode shapes should be fundamentally real. Okay? There are exceptions, but in this class right now, and can't do the super detail of everything, so let's just say that we anticipate that the procedure that I just explained about how you get from the mode shapes that are complex to the real modes will be such that what you have to discard from the imaginary is small. But let's say that you found, even though this phi3 had a small damping, that when you did this phi3, and this was the largest number, this number here was 0.2 plus 0.05i. That looks good. But this one here was 0.3 plus 0.2i. Then you might say, I'm not saying that's the structure, but something like this. You're going to say, this is a lot of complexity, right? The imaginary part is on the order of the real part. So this is also a reason to doubt the validity of the mode shape, and you might want to say, I don't trust this mode either. So even though I originally picked 8 for the order, after I looked at the damping and after I looked at my mode shapes after normalizing, I don't trust this 2 and I'm just going to keep this 2. So this is what we call the elimination of potentially possible computational modes. In the homeworks that I will be giving you now, that includes stochastic loads, stochastic ID, because the duration will be long but not infinitely long, or maybe not so long, the gaps that you will find in the eigenvalues, on the singular values, is not going to be as large. It may not be, I don't know because I haven't done it yet, it may be that the gap is actually pretty obvious anyway and that you don't have to discard anything. But you should know that in practice that might be something that you have to do. In fact, it's usually something that you have to do. That is, you have to over-select and then clean up. Not clean up, decide of your package that you originally selected, what is it that is worth retaining. Okay? All right, so that does it for this lectures.